Let's talk about the problem. If you have ever copy-pasted a function to swap one type, you know this feeling. Here's one that finds the largest value in a list of numbers. Now you want it for characters also, so you want to write it again. If you put them side by side, every single line is the same. The only thing that changed is the type. Like I-32 became the character or char. Now, this is the real logic. It's just duplicated to change only one word, but it doesn't seem sustainable or like best way of writing the code. But we're gonna talk about the better way of doing this. Take a look at this. This is the same function, the largest. Find the biggest thing in a list. But let's take a look at the signature. The T inside the angle bracket, that's one name standing in for any type at all. A placeholder that compiler fills in. Then this partial art, T isn't truly any type. It has to be one you can compare. We will explore more on that, the traits, soon. The body works on a slice of any T that holds that and returns one back. Here's the payoff. It's like the same function called with I-32 or F64 or string or even chars. One source, 4 specialized versions. It can be built with that. Now it's more like you write it once and call it with anything that fits the promise. Generics aren't just for functions. Over here we have a struct, point with one type parameter. T, both fields X and Y use the same T type or trait type. So a point holds two values of one type and here two integers. But what if X and Y should differ, like add a second name U? Now X is one type, Y is another. Same shape, two parameters, and here's an integer and a float, living within the same point. It's like the same shape, different fillings of things, types, and you pick the types that fits your use case. The part that you're gonna really like, because you have been using these generics this whole time, like from the last video, which is option. It carries one type parameter, T, and T is whatever the value might be there or might be missing, some of T or just none. And result carries two T. T for the value when things work and E for the reason when they don't. Okay for T and maybe error for E. You already wrote this. You maybe wrote this in a program or something. Generics were never really the crazy scary part. It's quite fun. We have seen the types. Now we're gonna explore the behavior, which is like a trait, which is like a promise about what a type can do. Over here, the grid says anything with this trait has a hello, and it names it and it doesn't write it yet. Then each type fills it in. Cat implements greet, its hello returns meow, Meowy, and that's the cat's version of the promise. The dog implements greet too, same method name hello, a different body, it barks, same call, different behavior decided by the type. And anything else can opt in, a robot, a teapot, whatever you write next. Just add the implementation. And the trait says what? The implement says like how it works. Now, we have seen how the method is like on the previous scene, but the threads can do a bit more than that. Instead of just naming hello, the thread can ship a body for it, a default, a fallback that every type gets for free, unless it wants something different. So cat can implement greet and write nothing at all, an empty implement or method. It just inherits the default hello from the thread, no extra code on the cat's side. Dog wants its own, so it overrides. It writes a hello that barks and that replaces the default just for the dog, and everyone else still gets fallback. It's like overriding when the type needs something different, otherwise, it just inherits. Now, let's get back to generics again, but with a new power, a bound. The T can be any type, but the moment your function calls hello on it, you have to promise that T can greet. So you write that promise in line. It's like the same promise written a second way, where like a clause after the signature, it reads the same, it just breathes a better once you start stacking several bounds together. And the third way drops the T entirely and write implementation methods on greet write in the parameter. Same bound, less typing, but we're gonna cover that more in a little bit. But a bound means that any T that can greet, not just one type. Simple trait is like a method, and in a parameter, it's pure shorthand. Notify takes an item that is some impl greet. That's the exact same thing as the generic bound from a second ago, like we did on the other scene, just a shorter read. In the return, it says something different. Make greeter hands back some impl greet. The caller knows it greets. The compiler quietly picks one concrete type behind it. But only one type at a time for a mix. You need din and you say that the compiler picks up the type. We finish up trace part. Let's look at something. So everything so far was static. One concrete type decided at each call, the fastest option. But sometimes you want a mix of all this, like a list with a cat and a dog in it, side by side. And for that, you reach for dynamic. Or in a short, you just said it, write this. Box of dynamics, that's like din, rates many types leave behind one reference. It's like a small cost, sometimes it's the only way. The deep mechanics are in like later on series 2, and it's like a rule that reach for the dynamics or DYN when you actually need a mix. Now, lifetime. Well, this sounds scary, but we kind of talked about this a bit in one of the earlier videos. Well, they look kind of scary. I mean, when you are reading a Rust code and you see lifetime, they look like really crazy, but trust me, they're not. Let's start with the problem. Here's a reference. R declared in outer scope is going to live a while. Now inside a smaller block we make X and point R at it. But X only lives inside that block. Watch what happens at the closing brace. The block ends. X is gone, but R still points at where x used to be. That's like a dangling reference. Reading it would be a bug. In C, this compiles and crashes later. In Rust, it should never compiles and it never does. How does the compiler checks that? You actually give it a name. Here's a function that returns the longer of two strings. The little trick is A in that name. It's not a duration, it's a label for a relationship. X lives at the least as long as the tick A. Y lives at least as long as tick A. The same labels on both inputs. And the output gets the same label. So the returned reference cannot outlive the input it came from. That's the whole promise. It's more like you don't say how long. You name a relationship that already existed. Here's a relief part. Well, most of the time you don't write tick at all. The compiler follows three rules. 1. Every reference parameter gets its own name automatically. 2. If there's exactly one input reference, its name flows to every output. So a function taking one string and returning one needs no annotation. And 3. In a method that borrows self's lifetime flows to every output, which quietly covers almost everything you write on a struct. The compiler guesses that for you, and it gets it right almost every time. Let's clear up one last concept. It's the tick static part. People read it as it lives forever and panic, but that's actually not the case. And here's what you have already seen it. Like every string literal in your program is a tick, but that's static. What it really means is that this can leave for the whole program, but if something needs it to, you can opt in by leaking a value. But that's rare and usually small, like it smells like. And tick static says it can outlive everything. It does not say it must. That's it. This whole episode is like you're not annotating a new behavior. It's more like you're naming relationships that already existed. And that's the lifetime way. And honestly, that's just the way for generics and traits also. That's it for the generics, traits, and lifetimes video. And this was really fun. And next time we're gonna explore closures and iterators. Thank you so much for watching. See you on the next one.